at LPI and was supported through the NASA Lunar Science Institute, and is now at the School of Earth, Atmospheric and Environmental Sciences at the University of Manchester. And she will be talking to us today about unraveling the temporal history of the moon. So Katie, whenever you're ready, take it away.
Thank you very much. I hope you can all hear me okay. Greetings from the UK. I'd like to say thank you to NLSI for inviting me to give this presentation to you all. It's a really nice thing to be asked to do. And I'd also like to thank my colleague Vera Fernandez, who I've asked to be a co-author on this talk, for facilitating discussions about the impact history of the moon through the ISI International Space Science Institute facility as well. Okay, so today's session is going to be talking about lunar geology through age dating processes, both from samples and from remote sensing observations of the surface, the photography of impact craters. So I hope that I'm just going to provide an introduction to this session, and then you'll get a chance to see all of the great talks afterwards. So the impact history of the moon is quite a controversial subject. Hello.
Katie, can you hear me? Can you start your webcam so we can see you as well, please?
Oh, I'm sorry. Hang on a second.
Okay.
It should be on. Is that on?
Yeah, push the start my webcam, and then there will be a little allow button after that you'll have to push.
Oh, I'm sorry.
I think you're coming through.
How's that
I'm
work?
just thinking about it.
I'll just keep going, and hopefully it'll kick in at some point.
Sounds wonderful. Thank you.
No? Okay. Okay, I don't know if that's working or not, but I'll keep going anyway. Okay, so I don't really need to give too much instructions for what a great place the moon is for studying a wide range of comparative planetology issues. And impact cratering and the timing of impact cratering cross-cuts all of these different subject areas, right through from the origin of planets like the Earth, a moon system, to understanding the history of the Earth and the effects of impact cratering on the onset and proliferation of life itself. Impacts also have an impact on the lunar environment, from the delivery of volatiles and hydrated materials to the surface of the moon, and the redistribution of those materials through impact bombardment and gardening of the lunar surface. Specifically today, I'm going to go into a bit more detail about the impact record. Is the webcam still not working? I'm sorry, this really isn't being that effective. Hang on a second. Let's try launching that again. Hey, there we go. Okay, I think we can see now. So, okay, let's move on to the next slide. So, the scientific context of the exploration of the moon was highlighted in the NRC document in 2007, where they revealed, they explored the issues about how the impact cratering history of the moon can help a whole range of different research topics. Specifically, the bombardment history of the inner solar system was highlighted as concept one on this particular scale. Understanding the impact cratering process itself is uniquely displayed on the moon to understand the morphology of impact craters, and also understanding regolith processes and weathering on airless bodies. And there are several key NLSI centres that are concentrating on these different research topics through groups such as the base LPI and SWIRI, and also the Brown Institute as well, and other NLSI projects. Let's move on to the next slide. So as I said before, impact bombardment is an incredibly diverse and sometimes controversial research topic. There's been a lot of large literature reviews of the different types of history to the lunar bombardment. But what is the actual evidence we're using to study this in a bit more detail, to understand how the impact bombardment rate has changed through time? Well, we can understand the age of the rocks themselves by studying the samples returned by the Apollo missions and the lunar missions, but also by samples that we have from the lunar meteorites that have been delivered to the Earth from a transfer process from lunar impact cratering processes. And from these types of samples, we can study both the age of the materials and also the chemistry of the materials to understand the types of material that's been delivered to the moon. We also have the imaging and remote sensing perspective, where we can study the morphology of impact craters and understand the distribution of basins on the moon itself. So these are impact craters that are bigger than 300 kilometers in diameter. And we think that there are between about 50 and 80 impact basins, and more are being revealed as more and more data has been returned to the lunar surface, both through imaging and geophysical observations of the crust itself. So it's by combining this knowledge that we've started to understand the cratering rate back through time, back from 4.5 billion years ago to the present day. And the diagrams at the top show a range of different impact bombardment models that we have and that are currently being tested by the types of evidence that we're collecting. And these models range from understanding that the impact flux of the lunar surface was controlled by the debris left over from the planetary accretion itself. There's evidence from the Apollo samples and that there possibly has been a spike or an enhanced period of lunar bombardment associated with about 3.9 billion years. However, we don't necessarily know the duration of this impact event. So there's a hypothesis that all of the impact basins could have been formed in such a short period of time as only 20 million years to a much longer 200 million year old age interval. So these types of models that have been tested by reanalysis of different types of samples. So to go over some of the sample perspective in a bit more detail and to understand some of the complexities, I outlined just previously how we have the evidence from the Apollo sample age dating data set. And these diagrams at the top of the screen here show you a comparison of the ages of Apollo samples returned from the Apollo 16 and 17 missions compared to the age dates that have been analysed from 3.9. But there's lots of questions associated with what this actual record represents, whether it's actually a genuine spike in the impact record of a very, very narrow period of bombardment, or could it represent only near-sized basins that were sampled during the Apollo missions, such as Imbrium, Serenitatis, and Nectaris, overprinting and dominating much older events? Or potentially, could all of these events just be related to the age dating of the Imbrium impact basin itself at about 3.9 billion years old? This is in direct contrast to the types of records that we've had from the lunar meteorites. And this was brought up yesterday during Bill Hartman's presentation about how the impact age record in lunar meteorite samples, so this is analysis of both the large hand specimens themselves and also class compared to the Apollo samples, in that we did have very few dates prior to about 4.2 billion years old and not many dates before about 3.9. And they don't necessarily show the same sort of impact spike that the Apollo sample show. However, there's several different interpretations of this particular record. Either it could be consistent with the idea that there is a cataclysm and that all of the previous older age basins were wiped out by events at around 3.9 billion years, or perhaps the record we're having from lunar meteorite samples is actually different to those by Apollo. To move on to some of the complexities in a little bit more detail before we move on to the cratering side of things. There's lots and lots of issues going on here. The assignment of the actual ages themselves to the basins from which we're sampling is under debate. These are topics that have been raised recently by papers such as Paul Spudis and Mark Norman in 2009. So the ages of the basins that we know are Imbrium at about 3.85 billion years, with a suggested new age of about 3.92 billion years. Potentially the Serenitatis impact event is about 3.989 billion years, which was sampled by Apollo 17, but as Paul Spudis has pointed out, much of the material that was sampled at Apollo 17 could actually be Imbrium rejectors, so the age of the Serenitatis impact stage itself is under debate. And then Nectaris, which has a range of ages between about 3.9 billion years and about 4.2 billion years. So until we can actually tie some of these issues down and identify basins and the ages that they represent, then this issue about the basins that we know we're sampling is going to not go away in any more detail. There's lots of issues themselves in terms of understanding what the sample ages are telling us about the events that they're actually dating and how this relates to both the isotopic reset of different impact rocks and the relationship to shock processes in rocks. Vera pointed out in a paper from earlier on this year that you can have lots of shock effects within samples that aren't necessarily impact resets. This is something we need to understand in a lot more detail. So the argon age dates are comparison to those that have been studied by zircon ages, which have been studied in situ in a bit more detail using uranium-lead impact dating. So an added complexity on top of all of these as well is the actual record we're looking at when we have a hand specimen in the lab that we're analysing, and the difference in maybe biases in the collection between analysing small glass and impact spheres compared to very small clasts and rocklets from the lunar regolith and then within lunar breccias compared to large hand specimens, and the relationship to the actual size of the impact that we're sampling and therefore to the significance of that impact event back through time. So to put all this together into a coherent type of plot, the different types of impact curves that have been understood from the types of samples we're studying is complex. And this is a nice diagram that David Kring made available on the PLSE Education and Resources website, just to demonstrate how poorly some of these things are still unknown. So whether the duration of spikes of a potential bombardment event, and understand the flux prior to 3.9 billion years is an incredibly important event to realise. And then understanding how this flux declines back to the past 3.5 billion years and how this relates to impact processes that could have affected the Earth is incredibly important as well. So these are big topics that we want to be able to understand. To relate this to the wider perspective in trying to calibrate some of these issues a bit more, there's an upcoming talk by Stuart Robbins later on in the session that I think is going to address this in a bit more detail. But it's just to point out that the relationship between the age samples and those types of complexities, and then relating that to the actual number of impact craters on the different surfaces that are being counted to try and calibrate this impact record back through time is highly complex and not well understood. So for example, in terms of these diagrams, the x-axis on the later cratering chronology is controlled by our lack of understanding of some of the age dates from some of the specific geological units that have been sampled, and the y-axis variability could be related to the subjectivity of impact cratering counts between different crater counting experts, and also the types of imaging and data sets that they've been doing. So fundamentally, calibrating the lunar crater chronology is vital, because not only are we using it to understand the geological history of the moon itself and the types of processes that are occurring, such as different cross-modification events, lava flow, emplacement events, and the magmatic history of the moon and other planets. But we apply this cratering chronology to the rest of the solar system as well. So it's vital that we address many of the issues that I'm discussing today to try and get to the bottom of this and really pin this cratering chronology down in a bit more detail. So to move on a bit to the other side of the talk, which is something that Amy Fagan's going to touch upon in her presentation coming up, understanding the temporal history and the timing of impact events itself can also be related to wider solar system dynamics. So understanding at those particular points in the lunar past where we may have had enhanced periods of bombardment, what are the causes of those events? Were they caused by asteroids impacting the lunar surface, by comets? And how potentially have those projectile sources changed with time? So adjusting these will then feed through and actually provide geochemical and temporal constraints for developing the types of dynamical models that Bill Bockey is going to talk about in a bit more detail in a little while. And all of these types of understandings have provide important information to understand the transfer of meteoritic material throughout the solar system, delivery of hydrated material and organic material to the Earth and in the solar system from the outer solar system. To get to this record, we can go back and we can study lunar samples in a bit more detail and really try and take apart and understand these types of issues. So to do that, we can get our hands on and study samples from the lunar regolith. Both the present-day lunar regolith, which was sampled by the Apollo astronauts when they retrieved soils and core samples from the upper few meters of the moon, and looking back further in the past, accessing paleoregoliths, so regoliths that were formed in the past, either by finding samples that have been trapped between datable units, such as the types of paleoregoliths and these rump discussed yesterday, or by studying ancient fused regolith breccias within the sample collection and taking those apart in a bit more detail. So to discuss how we're trying to address these issues through studying lunar samples in a bit more detail, one of the ways we can do this is by going back and looking at hand specimens of impact melts that have been collected by the Apollo astronauts. And by analysing these to understand the highly superficial element content of these in a bit more detail, from an isotopic analysis comparing the impact chemistry, the impact melt chemistry to the timing of the delivery of that particular impact melt. And Rich Walker's group has been producing a really nice group of data to suggest that the material that is being sampled by impact melts in the Apollo collection preserve a record of meteoritic material which differs from that we have in the present-day collection, suggesting present-day meteorite collection is being delivered to Earth, suggesting that there may have been a change in time of meteoritic material being delivered to the inner solar system. We can also study the volatile element content and compare this with the highly fissile element content of the lunar regolith itself to understand how volatile such as hydrated meteorites and comets were delivered to the lunar regolith. And looking back in the past a little bit, Everett Gibson and colleagues suggested that there's evidence of cometary or chondritic impacts in some of these lunar soils. And there are several groups now like that at the Open University that are trying to get back to address this issue in a little bit more detail. And groups that are using hydrogen isotope evidence to look at the glutinate chemistry to try and understand the sources of volatile material being delivered to the regolith. One of the pieces of work that I was involved with the LPI group was to try and understand the survivability of projectile material being delivered to the moon. So actually trying to understand if impact meteorite material can be delivered to the lunar surface and how that relates to survivability. And the good news is there are meteorite material that we found within the lunar regolith, both within the soils and the breccias by previous workers and by our study that was published last year. And so we can try and use this record of survivability of impacts to again tie that in with the highly physical element data to try and look back in the past to discuss at what points in time different types of meteorites were hitting the lunar surface. So I realise my time is short, so I'm going to skip past that and move on to advertising talks upcoming in the session later today that touch on many of these types of issues that I tried to very briefly run through. So hopefully you'll stick around and learn about some of these topics in a bit more detail. So the actual timing of the impact from studying crater counts of the lunar surface itself, and by going back and addressing some of the studying some of the samples in a bit more detail. Okay, so as a bit of an overview of the last slide, I hope I've tried to cover very, very quickly today the bombardment history of the moon. Its solar system is uniquely revealed on the moon, and understanding this record is really critical for understanding the impact record in the inner solar system, and especially the Earth. The Earth-Moon system is unique, and it has lots of implications for understanding how our own planet develops and how it's affected and changed through time. And there's lots and lots of complexities from not only understanding the actual record we have from the samples itself, but also understanding the record we have from the crater counting perspective. And so future exploration objectives should really try and address these high priority science areas for understanding the history of the solar system and comparative planetology between the Earth and the Moon. And I'd just like to say thank you very much to all the people that have given me the opportunity to be here, and I'll leave it at that and take any questions.
Great. Fantastic talk, Katie. Thank you so much.
I'm sorry about the webcam issue.
Not a problem. Not a problem. So I just had a quick question for you. You mentioned a debate earlier on with Mark Norman and Paul Spudis, and I was curious if you had a wish list of wherever you could go on the moon and pick up a sample to actually answer that debate. What would you pick up, and what would you hope to find? So if you I can hear myself on feedback, so I'm going to take that out. So if you want to really pinpoint the basin forming epochs, so the duration of when basins were formed on the moon, going back to sampling the oldest impact basin, South Wellington crater impact melt is probably the best place to do that. And I think this has been well established. I think David Kring's going to talk about this in a bit more tomorrow morning in his presentation. And here there are studies to go back and collect samples by remotely returned missions such as the Moonrise missions for the lunar far side. And I think most people would agree sampling SPA is a really high science priority. And sampling Nectaris as well, and trying to understand the age of Nectaris in terms of the near side impact crater basin formation, at least would be a great thing to do as well. Fantastic. All right. Well, if anyone else has questions for Katie, please enter them in the general chat.